So in this video, we're going to look at problem 3.10. And the first thing you'll notice is this looks very similar to the example we just did. In this case, we have a crate which has a known mass, which is going to allow us to calculate its weight. It's being supported by a rod, which is connected to some kind of joint at point D. At point D, that rod is tending to pull joint D down. However, there are two forces that are pulling it in the upward direction. One is directed along the line D to C. This is some sort of rod connection. It's pulling it up into the left. And from D to B, we actually have a spring. And what we're interested in knowing is if we know the actual weight of the crate, can we determine the actual stiffness of the spring if we know its unstretched length, and if from the geometry we can determine how much it's stretched. So if you think what's going on here, someone actually put this crate up here, and originally the spring wasn't stretched, and that weight actually fell down until the spring stretched enough to generate a restoring force to put the whole thing in equilibrium. What happens is we're observing in an equilibrium, so we can calculate how much the spring has been stretched, so we can calculate the marginal displacement. And what we're going to try to do is if we can calculate how much force the spring is actually exerting to keep this thing up, and we know how much the spring has been stretched, from Hooke's law, we'll be able to calculate what the stiffness is. So let's actually see how we would go about doing that. So I'm going to begin by just redrawing the actual drawing which was provided from the text. And the first thing I need to do, like always, is I need to identify a point in that assembly upon which the force of interest would act if I were to separate it from the actual drawing. And that's the process of drawing a free body diagram. So in this case, the actual force that we're interested in is the force that's exerted by the spring. So if you think about it, the spring will tend to pull this joint D up and to the right. So if I do the same thing that I did last time, and I just draw a segmentation about point D, right, that would involve the force that I want to solve for in this case, which is the spring force, which I need along with the stretched length in order to determine its stiffness. So if I draw a segmentation around joint D, I have to replace everything that I remove by an equivalent force that represents what I removed. So in the case where I actually cut here, we talked about in the last example that I'll replace it with a downward force that's actually equal to the weight of the crate. And when I cut at this point and this point, I will replace those by upward and to the right and upward to the left forces directed along the line of actions of dB and dC, forces of unknown magnitude that correspond to how those two connectors tend to pull the connection at D up. So when we take D away and separate it from the actual body, we have the weight of the crate pulling it down, and we have the weight of the two connectors pulling it one up to the right and one up to the left. So our free body diagram in that case, even though it technically has dimensions, since all the forces go through point D, we have a concurrent coplanar force system, so we can use a particle model. This will get really simple. Again, we know that the downward force that this rod actually exerts on the connection point D is the weight. That I did an example in the last video where I kind of justified that using Newton's third laws. So if you're a little bit confused, feel free to go back and watch that. And we have these two reaction forces where we don't know their magnitude, but we do know their direction. Particularly, we know that dB is going to be directed along the actual axis of the spring. And we know if we look at the geometry that we're provided, that the direction of the spring corresponds to, or it can be defined by an angle relative to the horizontal, where I can draw an equivalent triangle where the height is 2 meters, which I'm given, and the base is 3 meters. So if I know the force is directed along this line and I want to decompose it, our natural feeling is to get what this angle is relative to the horizontal. And I can get that by knowing that geometrically that spring is aligned along a line which completes a right triangle with a base of 3 and a height of 2. So if a right triangle has a base of 3 and a height of 2, its hypotenuse is given by Pythagorean's theorem, just the square root of the sum of the squares, or root 13. So I can actually express the sine and cosine of this angle. The cosine would be the adjacent side length divided by the hypotenuse, or 3 by root 13. And the sine of that angle would be 2 divided by root 13, or opposite divided by hypotenuse. So if I were to know the actual magnitude of the force in the spring, I could decompose it into a positive x and a positive y component by multiplying by the cosine and sine of that angle, which I don't know, but I do know the result of the cosine and sine respectively. So just always do a quick sanity check. If something is pulling up and to the right, its x component should be positive and its y component should be positive, which it is. For the force that's actually exerted on the rod connected from D to C, it's pulling up to the left. So it's will be decomposed into a negative x component and a positive y component. In order to find the angle which we will need to do the decomposition, I can know that that force is exerted along the rod itself, and that rod follows this geometry. If you notice, going back to the drawing, The rod is connected with 2 meters to the left displacement and 2 meters up, and it actually follows the hypotenuse of that right triangle. So naturally, if you have this angle here, and there's 2 meters to the left to go over to C, and then 2 meters up to go up to C, we know that this angle is just 45 degrees. You can actually compute it if you want, and I showed you Pythagorean's theorem there, but any angle that has the same displacement horizontal and same displacement vertical is just going to be 45 degrees. And hopefully by now we all remember, since it occurs so frequently, that both the cosine and sine of 45 degrees is just 1 over the square root of 2. So whenever this force that's being exerted by the rod is FDC, even though we don't know it, we can decompose it into x and y components by just multiplying both by 1 over the square root of 2, and remembering to put a negative in for the x component since it's directed to the left. The other force that we need to decompose is the weight. It's all going to be directed in the j minus j hat direction. So its x component is 0, its y component is minus mg. And for this all to be in equilibrium, this is the x component of the pull of the spring. So I just got it from going to the Cartesian form of this vector above. This is the x component of the pull of the rod. Basically what this equation says is those two must counterbalance one another if I put one on one side and one on the other. And in the y direction, what I find is that the portion that the spring pulls up and the portion that the rod pulls up has to counterbalance the weight. So you can solve this system of equations however you want. You can solve it by substitution. You can solve it by elimination. You can try your hand at the matrix vector techniques that I showed you in the last video, or Cramer's rule. But however you do it, you should determine that the force exerted by the component from D to B, which if you remember is your spring, has a magnitude of 495.19 newtons, carrying a little bit of precision to not introduce any rounding errors. And FDC has a magnitude of 582.68 newtons. So how am I going to use this to actually determine the stiffness of the spring? Well, this is the actual force that the spring is exerting. How can I relate that to the stiffness of the spring? Well, remember the way that a spring works. When you stretch it, it exerts a restoring force. So the first thing that we need to do, if we know how much force there is find out how much it's stretched. Well, if this spring is actually connected according to the geometry shown above, we can calculate how long it is when it's stretched, right? It's stretched 2 meters up and 3 meters to the right. So again, using Pythagorean's theorem, I can find that the length of the spring, and I'll just leave it in an irrational form, is the square root of 13 meters. So that's somewhere between 3 and 4 and closer to 4. And if you remember, we were told that the unstretched length of the spring was 2 meters. So what's happened? When that weight is connected, the spring is stretched in order to generate a restoring force to keep it all in equilibrium. So if I know how much the spring is stretched, and I know the restoring force that it's actually exerting, which I have here, I can compute the spring constant by simply dividing the restoring force by the length, which I can do. And if I make that computation, I get 308. Notice the units will be in the numerator, units of force, which is Newton, and in the denominator, units of meters. So this is in newtons per meter, as we would expect. And ignore my scratch there. I'm sorry. What happened was, again, I forgot that your homework actually randomized the answers. I should say the coefficients in the actual problem. So rather than solve this, I tried to take a shortcut and just look up the answer from the solutions manual. And then I remembered, oh, they're actually randomized. So I had to go back and put it into a simultaneous equation solver, but it should be consistent with the values in my PowerPoint now. And I try to always set the homework to not randomize the answers for you. So hopefully that's consistent with the answer for your homework as well.